In general, the word limit means something beyond which we cannot go. An athlete cannot run faster than 12 meters per second. The border of a country is a line beyond which a citizen cannot go, if he does not have a special permission. In mathematics, the dependent variable y of a function y equals f of x varies as the independent variable x varies. As the value of x approaches a fixed value x0, the value of y may or may not approach a constant value y0, which we will call limit. Our objective here is to define the concept of limit of a function. Let us consider a simple function defined as follows. The graph of this function is given in figure 1. In this figure, as x varies in the green interval, y varies in the blue interval. If the interval of x becomes smaller, the interval of y becomes smaller too. As x goes close to 1 from lower or higher values, y goes close and remains close to 0. Thus, as x tends to 1, it is reasonable to say that y tends to 0. This suggests the following definition. Definition 1. For a given function from a to b, let f of x be defined for all x with the absolute value of x minus a, positive and less than d for some positive d. We say that f tends to, or approaches, the limit L, as x tends to a, if for any given positive epsilon we can find a positive delta such that the absolute difference f of x minus L is less than epsilon, for all x with absolute x minus a, positive and less than delta. Let us give another example, the function g. Its graph is given in figure 2. If the value of x is restricted to the green interval, the value of y is restricted to the blue interval. The previous definition has the following characteristics. 1. It requires the value of f of x to stay as close as we want to the limit L, provided that x stays close enough to a. 2. It does not require any relation between the value of f at a and the limit L. In fact, f of a may not be defined. 3. It requires that f of x is defined at every point close to a, except perhaps at a itself. As an example, let us consider the function h. For this function the limit as x tends to 1 is 2 and it is different from g of 1, which is 3. The definition allows the limit L to be different from the value of the function at the point a. In the definition of limit, it is useful to understand the inherent relation between epsilon and delta. Although the value of x determines the value of y through the equation y equals f of x, it is the size of epsilon that determines the size of delta. In other words, epsilon is given and we want to find the delta that implies this epsilon. In figure 3 we have 4 variations of figure 1. As we go from a to d, a smaller epsilon is required. To achieve this result progressively, we need a smaller delta that will make epsilon smaller. We consider now the function k of x. This function looks like the function g and its graph is given again in figure 2. However, we observe that k of x is not defined at points with irrational x. Thus, the domain of k is different than the domain of g. Hence g and k are two different functions and this holds in any interval containing 1. In the figure, the interval from 1 minus delta to 1 plus delta contains values of x for which k of x is not defined, independently of how small delta is. Consequently, the third requirement of the above definition is not satisfied for the function k and we cannot speak about a limit of k of x as x tends to 1. To include this case we generalize a little the definition by using the concepts of deleted neighborhood and limit point. Deleted delta neighborhood of a point A is the set of all points x for which the absolute value of x minus a is positive and less than delta. Limit point A of a set capital A is a point whose every deleted neighborhood contains points of capital A. Let us give an example in figure 4. The set capital A contains all the points of the real axis from 0 to 1 included, and the isolated point 2. Every point of the interval from 0 to 1 included, is a limit point. The point 2 is not a limit point. Using the concept of limit point we generalize now the definition of limit as follows. Definition 2. Let f from capital A to capital B be a function and lowercase a be a limit point of capital A. We say that f tends to, or approaches, the limit L at A, if for any given positive epsilon there exists a positive delta such that the absolute value of f of x minus L is less than epsilon for all elements of capital A with the absolute value of x minus A, positive and less than delta. With this definition of the limit, the point x may approach point A only through points of the domain capital A of f. Thus, in both definitions, x tends to A and we observe the value of f of x. If there is a deleted neighborhood of A, which belongs to capital A, the two definitions are equivalent. If not, then lowercase a must be a limit point and only the second definition makes sense. If the limit of f of x, as x tends to A, exists, we also say that f of x converges to L at x equals A, and we write. If the limit of f of x, as x tends to A, does not exist, we say that f of x diverges at x equals A. In the previous definitions of the limit, the point x may tend to A in any possible way. In the special case, where x tends to A from lower values only, we have a left-hand limit. In the case, where x tends to A from greater values only, we have a right-hand limit. To calculate limit we follow two general methods. 1. We start from very simple functions and find limits using the definitions. We give an example. 2. For a more complex function f of x, we express the limit in terms of known simpler limits. We give again an example. In these calculations we can use the following general properties, assuming the limits of the functions f and g exist. 1. The limit of the sum f plus g is the sum of the limits of f and g. 2. The limit of c times f, where c is a constant, is c times the limit of f. 3. The limit of the product f times g is the product of the limits of f and g. 4. The limit of the ratio f over g is the ratio of the limits of f and g, assuming that the limit of g is not 0. With this presentation we define the limit of a function as the independent variable approaches a point,